All right, ladies and gentlemen, welcome back to section 4.3, day 1. We are talking about a very fun topic today, which is f prime, f double prime, and how these things relate back to the graph of a function f. So the first thing that's in this section is the first derivative test, but seeing as that we've already talked about the first derivative test, we're going to skip that, right? We know we use the first derivative test to find local maxes and local mins. We can also use the first derivative test to determine where the function is increasing and decreasing, right? So that's everything that the first derivative of a function can tell us about that function, right? But today we want to focus on the second derivative, and what that is going to tell us about the original function is its concavity. Okay, so new vocab term here. Concavity refers to the shape of a function. And there's two specific things that we're going to talk about today. We're going to talk about whether a function is concave up or if it's concave down. Okay, so the graph of a differentiable function y equals f of x is concave up on some open interval, which we'll call I. It could be any sort of interval that's a part of the domain of the function, right? If it's differentiable, that automatically means it's continuous, right? And so what does concave up look like? What does concave down look like? Well, let's start with concave up. And we're going to take a look at 3 different functions here that show us a mixture of concavities. Okay, so concave up is going to be something like y equals x squared. So y equals x squared, I'm going to zoom in here, right? Good old parabola. Okay, this is an example of a function that is always concave up. And so that's concave up. Let's look at a function that's shaped concave down, like y equals negative x squared. That's going to be an upside down parabola. Okay, so let's talk about what this actually means. So what does it actually mean for a function to be concave up other than looking like x squared? Well, the comparison I always like to make for this is kind of like a half pipe, if any of you know anything about snowboarding or skateboarding. And so I have a little image here that should hopefully help us out. I have to refresh the page here for this GIF to load. Here we go. Okay, so a half pipe is kind of like an example of a function that's concave up, right? And you can kind of trace along the side here, and you can see that a half pipe kind of looks like a parabola. And so this is concave up because if you look at the skateboard, what it's doing, right? It's always getting launched up into the air, right? It's always getting launched to the top, okay? Right? This is what concave up means. So imagine you're skateboarding or snowboarding, right? You drop into the half pipe. You're always going to get launched up as you go back and forth, okay? So this is kind of what x squared looks like, and x squared is considered always to be concave up throughout its entire domain, right? If you were to skateboard along x squared, you would always be getting launched back up into the air, versus y equals negative x squared, where, we have to defy gravity here in order to skateboard along a half pipe that were to look like this, but this would always launch you down in the air, okay, right? This would always launch you down, not in the air, probably towards the ground, okay? So one way of determining concavity is by looking at the first derivative of a function. So let's go back to y equals x squared, and let's talk about its derivative. So we'll do some more graphs here. So the derivative of y equals x squared is y equals 2x. And so this is another easy function for us to graph. This is just a line with a positive slope. And the thing we look for here is that the first derivative of x squared, again, which is this function 2x, this function is always increasing. Okay, if the first derivative of a function increases, that means that the original function, which in this case is y equals x squared, that function will be concave up. So you can determine concavity by looking at where the first derivative is increasing or decreasing for concave down. Let's look at y equals negative x squared. Its first derivative is negative 2x. Easy derivative for us to graph. That's a line with a slope of negative 2, right? And what do we notice about this line, right? This line is always going down, 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 right? It's because now we know what increasing and decreasing means, right? We should be able to look at a function and know when it's increasing or decreasing. So if I go back to my originals, y equals x squared, right, I'm not looking at where this graph is increasing or decreasing, right? This graph increases and decreases, right, over different parts of its domain. That's not what I'm looking at. I'm looking at where its derivative increases, right? Y prime is always increasing, and that's how we get that half pipe shape for y equals x squared, and the vice versa for y equals negative x squared. I don't look at where this function increases or decreases. I look at y prime, see that it's always decreasing, right? And so I can say that y is always going to be concave down, kind of like an upside down half pipe, okay? But here's the thing, right? We know that we can use the first derivative test to determine where a function is increasing or decreasing. So if I apply that to y prime, and this is where things get a little bit weird, what's the first derivative of y prime? Well, we call that y double prime, right? Y double prime is the first derivative of y prime. And if I want to know where y prime is increasing, then its derivative, y double prime, has to be positive. So let's see this in action. Let's go back to y equals x squared. Its derivative is y prime, which is 2x. What is its derivative? Y double prime is going to be just 2, right? Which is a horizontal line that is going to be above the x-axis, right? So this is always greater than 0. Where y double prime is positive is where y prime will increase, which is where y is going to be concave up. So let's apply the same logic to where y prime is decreasing. We can figure out where y prime is decreasing by looking at where its derivative, again, y double prime, would be negative. So let's follow along. Y equals negative x squared. Its derivative, we already did. Y prime is negative 2x. What is its derivative? Y double prime is just negative 2, which is a horizontal line that is always below the x-axis. So it is always negative. Where the second derivative is negative is where the first derivative decreases, which is where my original function is going to be concave down. And so on both of these examples so far, the concavity is constant throughout their domains, right? Y equals x squared is concave up, negative infinity to infinity. Y equals negative x squared is concave down from negative infinity to infinity. Our last example here has a mixture of both concavities. Let's look at y equals x cubed. Y equals x cubed, we should remember, looks something like this, right? And I'm going to bring this over just a little bit more symmetric. There we go. Okay, let's take its derivative. So its derivative is 3x squared, right? Which is going to be a skinnier parabola, but still ultimately a parabola. And then its derivative, y double prime, is going to be 6x, which is a line with a positive slope. Okay, so let me look at y double prime. So where is y double prime positive? If I look at this graph, where is it positive? Not increasing or decreasing. When I'm looking at y double prime here, I see that it's positive from 0 to infinity. And that is where y prime increases, and that is where y is concave up. If I take the right side of x cubed, it is going to look like the right side of x squared. And now let's go back down to y double prime. Where is y double prime negative? That would be from negative infinity to 0. That is where y prime is going to decrease, and that is where y is concave down. So if I look at the left half of x cubed here, right, it has the same shape as the left half of negative x squared. So y equals x cubed is an example of a function where the concavity changes. Okay, so a lot of the examples we're going to look at will have concavities that change. All right. Okay, so there's the intro to concavity. So what we're going to be looking at here a lot are functions that we typically can't graph. Or not can't, I should say, don't really want to graph, right? How can we determine the concavity of a function without having to graph it, right? That's going to be our focus, okay? So let's take a look at the next example here, and we can talk about the concavity test, okay? So the concavity test, we're going to take a look at a function that we can differentiate twice. The graph of a twice differentiable function, y equals f of x, is, and this is basically the same thing we said above, right? We want to see that a function is concave up anywhere its second derivative is greater than 0, and that it is concave down anywhere its second derivative is negative. So let's do an example. Let's determine the concavity of 3 plus sine of x over the interval 0 to 2 pi. Okay, and now the nice thing here is that this is going to work very similarly to the first derivative test. We're going to do the same 3 steps, but with a slight twist. Okay, so step 1, we still want to identify the domain. Well, that's given to us, 0 to 2 pi. So I'm going to write that in. Now, step 2 is normally where we would find critical numbers, right? We don't want critical numbers here, right? We don't want to figure out where the first derivative is equal to 0 or does not exist and look for sign changes. We're going to do all of that with the second derivative of our function. Now, in order to find the second derivative, we still have to get y prime here. So what's the derivative of 3 plus sine of x? Derivative of 3 is 0. Derivative of sine is cosine of x. And now we take the derivative again, and we get negative sine of x. And now I'm going to set these equal to 0 and does not exist. So from 0 to 2 pi, where is negative sine going to equal 0? So remember, 0 and 2 pi are not included because sine of 0 is 0, sine of 2 pi is also 0, but we don't want to include any of those, and so we only get x equals pi. Now normally I write Cn next to this before I circle it, but this is not a critical number, right? This is a possible place that the concavity could change. Okay, and now is any x value going to make sine not exist? Nope, sine always exists. So none for that. Okay, so step 3, right? This is where we make our table and do the first derivative test normally. We're going to do the same idea here, but we're going to plug everything into y double prime. So take x equals pi, split up our domain into two pieces, 0 to pi, and then we get pi to 2 pi. And now pick a number from each of those intervals and plug it back into y double prime. So from 0 to pi, I'll pick pi over 2. So what is negative sine of pi over 2? That is going to be a negative number. Pi to 2 pi, I'll pick 3 pi over 2. Again, I'm plugging it into negative sine, so sine of 3 pi over 2 is a negative, but I have to multiply it by the negative in front. Double negatives gives me a positive. And so I can look at these intervals and say that my original function y, which was 3 plus sine of x, is concave up from pi to 2 pi and concave down from 0 to pi. So ultimately, this work looks very similar to what we've been doing so far this chapter, right? But it's crucially important to understand why we have to do these steps at plugging everything back into y double prime, okay? If I want increasing or decreasing intervals, I use y prime. If I want to know maxes and mins, I use y prime. If I want concavity, I have to do this with y double prime. Okay, so let's use this work now to talk about a new idea, which is a point of inflection. So lucky for us, we're going to be able to use a lot of the work we just did in order to talk about this. But here's what we got. So a point of inflection is a point where the graph of a function has a tangent line. Now, I'm going to reinterpret that to just mean that f prime of x is going to exist at that point. So this is a place where the first derivative exists, okay? But more importantly, and this is the crucial part, this is a point where on the graph of some function where the concavity is going to change, okay? Right? It is a point on your graph where the concavity changes. So let's find the point or points of inflection for y equals 3 plus sine of x on the interval 0 to 2 pi. So let's go back up here, and lucky for us, when we want to find a point of inflection, we can use all of this work again. And the only thing we really need to determine is does the concavity change somewhere over this interval? So we don't need the last part here for my answer, right? The only thing I want to focus on is, right, does the concavity change? Yes, it does. Well, where did the concavity change? The concavity changes at x equals pi. So my point of inflection, now this one is called a point, but when you write your answer for this, you actually only need to give me the x coordinate, okay? If you want, you can take pi and plug it back into the original curve and evaluate it, right? And get the y coordinate that goes with it. But really, when I ask you for a point of inflection, you can just give the x coordinate, okay? At x equals pi is where the concavity is going to change for this function 3 plus sine of x, right? So you're looking for a sign change. So this is kind of like doing a local max or a local min, right? If the second derivative, goes positive to positive, not a sign change. Negative to negative, not a sign change, right? But unlike finding a max or a min, we don't care like specifically if it goes positive to negative or negative to positive over an interval, right? We only care that there is a sign change. So let's take a look at a bit of a tougher example now of finding a point of inflection. So y equals e to the negative x squared. Okay, so e to the negative x squared, right? We're still going to go through our same steps here like we always do. So step one, we need to figure out the domain. Now, lucky for us, an exponential function, the domain is going to be all real numbers, right? X can be anything. You can square it, multiply it by a negative. You can take e to a negative exponent. That's no big deal, right? So we're going to get all real numbers. Okay. Step 2. First, we have y here, right? We need to start off with the first derivative. And e to the negative x squared derivative of an exponential is always going to be itself. But we have to do the chain rule, so we have to multiply by the derivative of the exponent, which is going to be negative 2x. And so I'm going to rewrite this as negative 2x e to the negative x squared power. Okay, now, again, just like the last two examples, right, we don't want to find maxes and mins here, right? So we need to figure out the second derivative. Okay, so for the second derivative here, right, negative 2x e to the negative x squared, right? Well, this is actually just a product, right? So I'm going to use product rule to take its derivative. So let's start off with e to the negative x squared. And I'm going to multiply that by the derivative of negative 2x, which is negative 2, plus, now I'm going to go negative 2x times, and now here's the thing, right? What's the derivative of e to the negative x squared? I'm trying to take the derivative of this part of y prime. Well, that part is the same as the original, right? So what was the derivative of y? Well, we already figured it out, right? It was negative 2x times e to the negative x squared. So I'm just going to write that down again. So this is kind of a weird product rule, but this is the second derivative. So I'm going to do a couple of things here. I'm going to rewrite this as negative 2 e to the negative x squared. And then double negatives there, so I'll get a plus 4x squared e to the negative x squared. And normally I don't do this, but in these questions, and the same is true when we're trying to do the first derivative test as well, I know I'm going to be solving an equation with my y double prime here, right? So I'm actually going to factor this out. I'm going to factor some stuff out of here. So each of these terms has a e to the negative x squared that I can take out. So I'm going to do that. I'm also going to divide by a 2. So I'm going to take out a 2e to the negative x squared from each of those terms. And so that is going to leave me with a negative 1 plus, and now I'm going to have 2x squared left here. And so I'm going to set y double prime equal to 0. I'm going to set y double prime equal to does not exist. Okay, so let's set this equal to 0. So now, lucky for us, if I'm applying my zero product property to this, right, I can just set each of these factors equal to 0 separately. So again, lucky for us, 2e to the negative x squared, right? If you have any sort of exponential, can that ever equal 0? Can e to some power ever give you 0? Right? It doesn't matter what the exponent is, right? E to some power will never equal 0. So I can just flat out ignore that. And now all I have to do is set the parentheses part here equal to 0. So negative 1 plus 2x squared equals 0. So I'm going to get 2x squared equals 1. So I'm going to get x squared equals a half. And so I'm going to get x equals, and I'm going to go ahead and rationalize this, and I'll get plus or minus root 2 over 2. So these are two possible points of inflection. Okay, and now for the easy part. Anything make this not exist? No. right? Exponentials, domain is all real numbers. Quadratics, domain is all real numbers. This function, y double prime, I'm just multiplying them, right? And so nothing from that. And I will cross that out. Okay. And so now I have my two possible points of inflection here at plus or minus root 2 over 2. And so I'm going to use these and split up my domain into three pieces. And so step 3 I'm going to do up here to the right because I'm out of room. I'm going to have negative infinity to negative root 2 over 2. And then I'm going to have negative root 2 over 2 to positive root 2 over 2. And then positive root 2 over 2 to positive infinity. Okay, so pick a number from each of these intervals, and I'm going to plug it into y double prime. Okay, so from negative infinity to negative root 2 over 2. So negative root 2 over 2 is not a number I expect most of you to know, right? So if you want, go ahead and pick something that you know is definitely not negative root 2 over 2. How about negative 50? Okay, and now we're going to plug this into y double prime. I always like to plug things back into the factored form here. And there's some good news with this, right? And the reason why I want to plug into the factored form is because I can just flat out ignore the part here that's been factored out, right? E to any power is going to give me a positive number, so I can just ignore it. So y double prime is going to be positive or negative based entirely on this parentheses here. So 2 times negative 50 squared, well, negative 50 squared is positive, times 2 is making it even bigger. If I take 1 away from that, this is still going to be a big positive number. Negative root 2 over 2, comma, positive root 2 over 2. I can always pick 0 there, which is good. Again, I can ignore the first part, right? E to the 0 is 1, which is a positive, right? I don't need to worry about that. Plug 0 into this parentheses, 2x squared drops out. I'm left with just a negative 1, which is entirely negative. And then root 2 over 2 to positive infinity. I'll pick positive 50, right? Again, ignore e to the whatever power. That's going to be positive, right? 50 squared, big number, times 2, even bigger. Subtract 1. That's still going to be a positive number. Okay, so what is my concavity test showing me here, right? It shows me, right, that this function y starts off concave up. At negative root 2 over 2, it is going to switch to concave down, right? And then at positive root 2 over 2, it switches back to concave up. So 2 places where the concavity is going to change. So I have a point of inflection at x equals plus or minus root 2 over 2. So both of those gave me points of inflection. Okay, so it's all about where does the concavity change signs. That's the main thing you want to focus on here. Okay, now we didn't really talk about it, but if we go back up to the definition, remember, right, f prime should exist at that point as well. So, you always do want to take your potential points of inflection, right? Can you plug them into y prime? Do I get anything wrong here? Basically, are those x values in the domain of y prime, right? So that's something else you want to check for as well, okay? But the main thing here is going to be doing the concavity test. Okay, so we're going to stop right here, and I will see you all next time.